This video is going to cover graphing exponential functions, which is our learning target 4 in our unit on exponential functions. As a little review and lead in to what the graph of an exponential function looks like, let's revisit some of the more simpler graphs that we did earlier in the year. Y equals x. This is a linear function. It makes a line when we graph it. Y equals x would be graphed by plugging in 0 for x, meaning y is equal to 0, 1, 1, 2, 2, 3, 3, and so on. Linear functions, just like their name, graph lines. Y equals x squared is a quadratic function, and when we plug those in, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and that is how we end up with a parabola. Today, what we're going to talk about is y equals 2 to the x power. That x is now an exponent, making this a exponential function. They also are curves just like the parabola of a quadratic function. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and we end up with the curve of an exponential function. I just want you to see these side by side so you can get a feel of what these look like. They're curves, much like a parabola, but they do increase very, very quickly. So what is exponential growth? Exponential growth is a function with a r greater than 1, like y equals 2 to the x. In this problem, our r is equal to a 2. Exponential growth graphs look like this. They look like they kind of ride the x-axis, being very, very close to them, and then quickly increase very rapidly upwards, getting very steep very quickly. This is what exponential growth looks like. What is exponential decay as a graph? That's a function where the r value is between 1 and 0, such as this problem, where our r is 1/2. This is the image of a exponential decay graph. It's a graph that drops very, very quickly, and then it ultimately looks like it's riding along the x-axis. It's not. It doesn't actually ever touch the x-axis. It just gets closer and closer to it. So what's the best way of graphing? Well, making a table is probably the best way to graph. We're going to plug in a bunch of x's and y's in order to come up with the shape of our graph. Let's make sure that we include both positive and negative numbers as we're graphing. So starting from -2, -1, 0, 1, 2 usually is pretty good for getting the general shape of a graph of an exponential function. If I plug in -2 into the x, I get approximately 0.05. If I plug in -1, I get approximately 0.17. If I plug in 0, I get 0.5. If I plug in 1, I get 1.5. If I plug in 2, I get 4.5. So now let's plot these. -2, 0.05 is very, very, very close to the x-axis. Very close to 0. -1, 0.17 is a little bit higher. 0.5, a little bit higher. 1, 1.5, 2, 4.5, and so on. Now let's sketch this out, and this is what my exponential function looks like. Do notice a couple things. 1/2 is right here, which is our y-intercept. It's our initial output, and you should always easily be able to find that wherever the y-axis gets intercepted by the graph is where our a is going to be. Let's try this one more time for another. Again, let's do a variety of x's. So let's do -2, -1, 0, 1, 2, and let's go up to 3 this time. When I plug in -2 into my function, I get 9. When I plug in -1, I get 6. 0 outputs 4. 1 outputs 2.67, 1.78, 1.19. Let's plot these. -2 goes up to 9, 1, 6. 0, 4, 1, 2.6, it's close to 2.5, so approximately there. 2, 1.7, a little bit higher than 1.5. And 3, 1.19. So this is the shape of my graph. The more x's you plug in, the better an image you're going to have once you sketch it out. So make sure you include a variety of x's so that you get the best sketch possible. This graph is an example of exponential decay because going from left to right, this graph does decrease going down. Let's try working backwards. Let's look at the graph of a function and see if we can determine what the actual function is. Here's the important pieces to look for. First off, where's the y-intercept? In this problem, it's at 4. So that means I have an a of 4. Other important things to find. Let's find a couple of different outputs. Let's find an output for 1. It's at 8. Let's find the output for 2. It's at 16. Since we know two outputs, I can definitely find an r. That's like looking at a table. I plug in 1, I get 8. I plug in 2, I get 16. So what's the r by doing 16 divided by 8? It's 2. So my r value is 2. Now that I know both my a and my r, I can actually write my function. F of x is equal to 4 times 2 to the x power. Let's try that one more time. Again, first off, find the y-intercept. The y-intercept in this problem is right here at 3. So my a is equal to 3. Let's find a couple of outputs. When I look at 1, I can't really exactly tell where this point is at x equals 1. So I'm not going to use that point. Let's find some better ones. How about we go over to negative 1? Negative 1 hits 6 on the y. Negative 2 is at 12. So when I add those to my table, plug in negative 2, I get 12. Plug in negative 1, I get 6. So 6 divided by 12 is 1/2. So my r is equal to 1/2. F of x is equal to a, 3, times r, 1/2, to the x power. Don't forget your parentheses around your 1/2 because you do want to say that this x applies to the 1 and the 2 and not just the 1. Real quick, let's try that 2 more times. Locate the a. In this problem, it's at 2. When I plug in 1, I get 4. When I plug in 2, I get 8. So I am doubling from 4 to 8. 8 divided by 4 equals 2. That's my r. So my answer is f of x is equal to 2 times 2 to the x power. In the next graph, 2, which is my a. So an a of 2. Find some other points. Negative 1 hits 6. Negative 2 hits 18. 6 divided by 18 is equal to 1/3. So f of x is equal to 2 times 1/3 to the x power. That covers our examples for graphing exponential functions as well as writing functions from their graphs. If you have questions, make sure you write them down, bring them in the class. Don't forget to click forward, answer the questions, and hit the submit button.